Right, so I wanted to clarify a couple things with you guys today. First and foremost, what I'm going to get to mainly today is talking about a position versus time graph. Now you're going to see over here I have a different thing too, a speed or a velocity. Normally it's velocity versus time that we're going to be using most. But this is the main graph we're going to start out with because this is the basis of all of it, okay? You measure a distance, you measure a time, and you end up with this graph right here. Now, it seems like it's pretty straightforward, and it generally is. But to discuss this, we have to start talking about things like position. So that would be an x and a y coordinate, like Descartes, right? So where you're at in your x and y position. We also have to talk about distance and displacement. So how far you've gone versus how far away you started from your start point, right? So did you end up near where you started, or did you just end up farther away? Displacement is the total distance you've ended up from where you started. Displacement is just, distance. Distance is just the total distance that you've gone, okay? So, if we talk about this, let's look at an example here, okay? When you talk about this, first thing to notice about this kind of a graph is that in physics, we love to put time on the bottom axis. You guys are normally, when you've seen something graphed out, you've normally seen an X down here and a Y up there, right? Well, that's because you've been dealing with a three-dimensional universe, X, Y, and Z. Turns out it's a four-dimensional universe, and we actually have time. And the things about physics that we really care about almost always vary with time rather than with position, okay? So what we're going to be looking at is how the position, or the velocity, or the acceleration, changes as time goes on, okay? Without time, you can't have any motion. So, let's think about this. What we have is if we have a person that walks from A over to B, okay, and let's say that's a distance of 10 meters, and let's say it takes a certain amount of time to get from A to B. Let's say it takes, let's put it in seconds, how about that? Let's say it takes 60 seconds, okay? And that way we end up with a really kind of an interesting unit here, okay? So if we go 10 meters from A to B, and we do so in 60 seconds or 1 minute, what is our speed going to be? Okay, well remember this, our speed, when we talk about speed, if you look at something on a car, right, the odometer on a car or the speedometer on a car, what you'll see is that speed and velocity also are measured in things like miles per hour or meters per second or feet per second or kilometers per hour. All of those things a distance over a time. And in fact, if you look at the units are actually telling you the equation here. So with speed, you actually put your distance, okay? And it's key that you notice this. Speed is distance. Distance, not displacement. Distance over, and then seconds or hours or minutes or whatever on the bottom. So that's over time. So speed is a distance over a time, okay? So when you're driving your car, it's giving you this reading, an instantaneous speed, whenever you look at that speedometer, okay? So if I plot this motion onto a graph, okay, we have time down here, we have, meters or, x distance up this way. We're only traveling the x direction. So if we plot 60 seconds out, let me put 30 here, and, I'm just going to go 60 for the first spot. How about that? 60 seconds, units in seconds. And then I went 10 meters. So my first line here is 10 meters, okay? So I went up 10, and I went over 60 seconds in time. So for my first leg of this journey, I have no other information between, so I have to draw a straight line from 0, where I started, 0 time and 0 position, over to 10 meters, and it took 60 seconds to get there, okay? So not too interesting, right? But what I want you to notice is that if we're talking about this in position versus time, position is a vector quantity, okay? It is a vector quantity. So this is actually, we're going over plus 10 minutes. If we're going to use the regular, plus direction for this, for x would be to the right. In math, that would be our convention. So if we went this way, we go plus 10 meters, okay? What I want you to now think about, if this is your house, this is your friend's house, you walk to your friend's house, later in the day, you turn around, you reverse that course, and you go back. So I'm going to draw this, I'm going to draw it below it, even though it's the exact same path, so you can actually see it. It still takes 60 seconds to get back from B, your friend's house, back to A, your house. The distance was still exactly the same. It was still 10 meters for the distance, but we're going in the left direction according to our coordinate system. That means we're going minus 10 meters. So when we go to plot this out, now all of a sudden we start out at plus 10 meters, we end at 0 meters here, right? So we've gone from plus 10 at our friend's house back to our house, which was 0. And we've done it in another 60 seconds, so that would be 120 if they didn't stop, right? So we go from here back to 0, and we've gone back to our house. This may interest you, because notice that this thing flips around on itself. We went plus 10 meters, then we went back 10 meters, minus 10 meters, okay? So what distance did we cover? For measuring distance, this is key, okay? If you're measuring distance off of a position versus time graph, you have to measure each length of this line and add them up, okay? So if we want to know distance, what distance? Distance, I'm going to erase this, okay, so remember this up here, okay? We're going to come back to that. You can rewind the video and find that. Okay? So what distance did we go? Well, we went 10 meters there, and later on we went 10 meters back. That's also 10 meters. Add those together, and you get your total distance, which was 20-meter travel distance, okay? But what about our displacement? And remember this, our displacement is how far we ended up from where we started. So our displacement is actually read right off of the graph. Our final displacement is where the final point is. So in this case, you start from 0 meters, you go up, but then you come back down, so your total displacement was just 0 meters. And how in the heck does that work? Because remember, distance is a scalar, it has no direction, okay? But displacement, on the other hand, displacement does have a direction. We went plus 10 meters, and then we add to that what we did the second round, which was we went minus 10 meters. So you end up with 0 meter displacement. So in this instance of somebody walking from their house to their friend's house and then back home in the same exact amount of time, covering the same distance of course, you end up with 0 displacement because they ended up where they started. However, your distance, if you were driving it in a car, your odometer would keep ticking up and up and up and up, right? You've actually covered that distance. You may have started and ended at the exact same spot, but you could have gone around and around and around and around in a loop to end up where you started, okay? Displacement here is a vector quantity. So where did you end up? Well, from 0 to 0, 0. But our distance, we went plus 10 and then we went minus 10, so we actually went 10 and 10 for a distance, total distance of 20 meters. Very different things, okay? Now, I'm going to go back to that speed thing that we had written up here, remember? We wrote that speed was a distance over a time, okay? And our displacement comes into a vector quantity, so speed has no vector, right? It has no vector whatsoever. It is a scalar quantity, okay? But what about our velocity? Velocity is a vector quantity. It does have an arrow with it. It has a direction, okay? So velocity is displacement over time. So what you'll notice in each case is that you have an x over a t, okay? That's actually your equation for your speed or your velocity, but the velocity, of course, remember that the x for velocity is going to be a vector quantity, whereas this, for the speed, is just a magnitude, okay? And that's what those two lines there mean absolute value of. It has no direction, okay? So, but if you look at this, this is distance over time, right? Or distance is on this axis, so that'd be our rise, and time would be our run, wouldn't it? So it turns out that velocity on this graph is actually just the slope of this graph. So for this graph, if you look at this first piece right here, this time right here, right, we have a positive slope, okay? So if we want to know our velocity, for the first piece of this graph, you will get a plus 10, right, plus 10 meters over 60 seconds. So you will get a 1 over 6 velocity, 1/6 meters per second, okay? What about on the back side of it? It's the same distance, isn't it? But now we're going in negative direction. So our velocity here will be minus 10 meters over also 60 seconds, okay? So we will have a negative 1/6 velocity. Same magnitude, so it has the same speed, okay? It has the same speed, but it has an opposite direction. So is that always going to be the case? Is speed always just going to be the magnitude of velocity? In a lot of cases, that will be what you see, but it's not always the case. And I'm going to show you the weird case here, okay? So let me go ahead and erase this real quick. Okay, I'm going to try and keep this up, and I'll rewrite those two equations so you have them, okay? So speed was magnitude of our position, right? No direction to it. Plus and minus is taken out with that absolute value sign over time. And velocity was just straight up x over t, okay? I'm drawing this out so it's a square. This has got x's and y's. I don't want to get overly complicated, but again, drawing things that are overlapping are hard. So just imagine this is actually all in the x direction. You know, do it x and y. It doesn't really matter too much, okay? On this instance, I want to show you the difference between distance and displacement and speed and velocity, okay? So let's say you are going to go walk around your block. You start from the edge of your yard, okay? Your house is actually right here is your house. But you're already on the edge of the yard, and that's where you start your walk, okay? So here you are, dawdling along, 4 meters up, 5 meters over, 5 meters back down, and 5 meters back this way, right? So how much ground did you actually cover walking around the block, okay? Well, the ground that you covered, right, that would be your distance, wouldn't it? That's how much you felt like you expended. The effort you expended to go all the way here, around this, would be you went 4 meters up, right? So remember, these are absolute values. They have no plus or minus to them. That's why I'm writing this way, okay? So you went 4 meters, then you went 5 meters, then you went 5 more meters, right? And you finished up 5 meters, right? So what distance did you actually cover? You covered a total distance of 4 plus 5 plus 5 plus 5, that's 15 plus 4, so it's 19 meters. You covered 19 meters in your distance. That's how far you actually went. And let's say it took a total time travel was, let's say 120 seconds. You did it in 2 minutes. You're going fairly fast. 120 seconds, okay? So what would your speed be? Now remember, speed is distance over time, okay? So speed is going to be 19 meters, total distance without any, plus or minus vectors to it, right? You went 19 meters over 120 seconds, okay? But what about your velocity? What was your total velocity? Well, remember, your velocity was displacement over time. Displacement's a very different thing. Because remember, displacement is just how far away you ended from where you started. Well, you started here, and you ended here, right? So this right here, that is your displacement. And it turns out, if you add them all together, you'll have a plus 4, plus 5, right? And then you'll have a minus 5 and a minus 5. So you'll actually end up with a total displacement of minus 1 meter. You actually went backwards, or in this case down, right? 1 meter. So your velocity, so total displacement was plus 4. And again, remember, I'm just basically saying that you're going in the x direction. I'm just showing it for, this way so you can kind of see it a little bit easier, okay? We went plus 4, plus 5, minus 5, because you're now going down, and then minus 5 more, which gets you to a total displacement of minus 1 meter. So what will your velocity be? Velocity is equal to displacement over time. So your total displacement was minus 1 meter over 120 seconds. So now in this case, you can see, is your speed always just the absolute value of your velocity? No, because the absolute value of this guy would be 1 over 120 meters per second. Whereas our speed was actually 19 over 120 meters per second. So they can be very different things. They can be absolutely very different things depending on what sort of a route you follow, okay? And how far away you end up from your starting point. What if you're just going this straight line and staying that way, right? You're just on your first leg of your journey to your friend's house and nothing else, right? You go 10 meters, you go that in 60 seconds. In that case, your velocity and your speed are going to be the exact same. They're going to be the exact same thing because they're both going in the same direction and you're going in a straight line and you're ending some distance away from where you started. All of your effort went into getting there, okay? And you didn't double back at all. So therefore, in this instance, your speed and your velocity do the same thing, okay? So hopefully that helps you to kind of understand the differences between the two, but remember, key things here, okay? Velocity, let me erase some of this here, okay? And again, you can rewind the video if you need to kind of like get an idea of this again. But your velocity is your displacement over time. So that's going to be our x position in this case, over time. And again, that's just straight up plus or minus x position. Speed, on the other hand, is going to be distance over time. And since distance has no direction, it's really just going to be the absolute value of your position over time. Okay? And when you're reading things off of this graph here, if you want to know your velocity, it will be the slope of the line. Positive slope means positive velocity. Negative slope means negative velocity. Speed has no direction, so the slope of that line for your instantaneous velocity, the velocity for each little piece, right? The slope of that line will be your speed, just without the plus or minus to it, okay? You want to know your total speed, you add up all of your distances, all of your times, and divide them, right? Distance over time. You want to know your velocity, you find your displacement, and you divide it by time. And they can be very, very different quantities.